Are you working with high-dimensional data? Do you want to use it for machine learning purposes and all these data points are just too hard to fit into your model? Or potentially you just want to plot your data into like a two-dimensional plot and kind of get a general idea of your data. Well, in this case, there is a method called PCA, Principal Components Analysis, which can help you in these applications. So maybe you can help me explain how this method works. What do you think? Okay, excellent. So let's get to it. So before we start, I just want to briefly talk about the weird things that happen in the geometry of high-dimensional spaces. So there's something called the curse of dimensionality. And a lot of people have a different idea of what it means. But it basically means is that if you have a lot of dimensions, it's a pain in the ass. Here's an example of a hypersphere and a hypercube. So those are basically just generalizations of the idea of a circle and a square. So if you imagine that we have a cube and a sphere that fits inside that cube, in a 2- or 3-dimensional case, it's pretty straightforward. But on higher dimensions, this is quite strange. So these are the generalized definitions of the volume of those objects. And one of the properties is that if you increase the dimensionality, the volume of those two objects behaves very differently. So here's an example of a hypersphere that has a radius of 1. And the same for the cube with a radius of 1. So we can see that the volume of the cube grows exponentially, while with the number of dimensions, the volume of the sphere actually shrinks. And so what does this mean? This means that all the volume, the difference of the volume of those two objects is in the corners that the sphere does not take in. And realistically, if you calculate the distances between high-dimensional objects, it means that all your high-dimensional objects will be on the edge, like in the corners of this figure. And then if you calculate the distances between objects, they all end up having kind of the same distance. So this is just a very brief geometric explanation of this problem. Sometimes we can use methods like dimensionality reduction to help us in analysis of high-dimensional data. So I want to kind of explain this with the help of a very simple observation that we want to make. So in this case, we have a monkey that is sitting on a spring. So this monkey is hanging on the spring, and the spring is moving up and down. So the monkey is moving in one dimension. So this is this y coordinate, up and down. And if this is like in 3-dimensional space, he does not move in either the x or the depth, right? It's only up and down. So imagine we want to observe a dynamic like this. So we install a bunch of cameras. So we call them C1 to C3. And they watch the monkey move, right? So now if the monkey moves, they will generate images. And so each camera produces a 2-dimensional picture. So here is the cameras. And as I said, they produce data points over time. And so they write down the position of the monkey with x1 and y1 for camera 1 and so on. So now we have all these measurements. And we have, this monkey going up and down. So now when we watch this, we record the position of the monkey at each time point. So each time point that we measure now can be described as a 6-dimensional vector. We have 6 measurements, 2 from each camera. There we go, right? So each time point is a 6-dimensional array. So the problem with this is that we have a lot of redundancy in our measurements because the true dynamics can be described on a single dimension. It's the up and down dimension, right? So this is the only thing that really changes in our data, even though the cameras recorded 6 dimensions. And so this has to do with the redundancy in the data and the redundancy in the dimensions that we have. So imagine this. If I have a giraffe and the giraffe moves up and down, so if you look at the camera now, okay, the position of the giraffe only changes in this axis, right? It's only changing on this axis. But it's not changing here. The giraffe always stays at this point. So there's really no information in this dimension. Now, I can take the same camera and I can tilt it. So now the camera is tilted and I'm still just moving the giraffe up and down. So I'm not like changing anything. Right? So the giraffe is going up and down. So now in this dimension, this is changing, right? But now also this is changing. Like if you look here, I'm moving up and down because there's an angle to the camera. The X dimension is now also measuring the giraffe. So even though the giraffe really only moved in one dimension, we could show that both dimensions of the camera were capturing changes. But this is because the dimensions are not independent of each other. And so here's a small example of this. So if you look on the right side, there's a high redundancy between the X and Y variable. And basically X explains everything Y is doing. If we only know X, we know what Y is. But if we look on the left, that's not the case. If we have a single point of X, Y could be anywhere. So we don't really learn anything else. So we would have to really look at both of these dimensions to understand what's going on in our data. So the principal components analysis, and I just briefly go over this, has a couple of assumptions. And usually people are not really taking this too seriously. But what you have to be aware of is that you can only capture linear dependencies between your dimensions. So only things where you can fit a straight line through are really captured by this method. And then they also require the data to be normally distributed, which oftentimes the data is not. But in general, this works still pretty well if the data is not normally distributed. So don't worry too much about this. And then another thing is that this method really emphasizes the large variances in your data. So if this is not actually what you're interested in, then this method might be problematic because it ranks all your principal components later by the variance that they capture. And then another thing is that in the end, once we do this, we will create a new dimensional space. We rotate our space around. So it turns out that then the dimensions are orthogonal to each other. So they're independent. There will be no two dimensions that carry the same information. Okay, so very simple example here. We have a two-dimensional data set and we have points in orange. And so we can see that there is a correlation between these two dimensions. So we could fit a line through here, right? And so what is this data, right? So it could be anything, right? So in this case, we have temperature versus ice cream sold. So imagine you are a store owner and you want to know how much ice cream you sell depending on the temperature outside. If the temperature is high, you expect to sell a lot of ice cream, and this is what you see in the data. On hot days, you sell a lot of ice cream. And in cold days, you sell very little ice cream. So there's a natural correlation between these two variables. And each measurement would be a point or a sample in your data set. You can have even more high-dimensional data. So this is only a simple example, but realistically, you would have thousands of dimensions. For example, gene expression. A biologist, they measure the expression of genes, and a human has about 22,000 genes. So each sample, you would measure all the genes, you would have 22,000 dimensions. So let's go back to our example. So what we can do is we can fit this line, right? So we see there's a correlation in our data points. So we can draw a line along our data points. And so what we can do now is we can project our points onto that line that we found. And the method really wants to find a line that maximizes the variance of our data. So we want to kind of find the line where the points are most distributed evenly over that line. It is equivalent to finding the least square fit from this. So this is similar to any regression model. So now we project the data points onto this line. And so this line has an origin. So the data has to be centered. I omitted that step. But so we see that our line goes through the origin. And so now we can describe the projected data points, where they fall on this line relative to the origin. So now we have a new dimension. We call this x prime. This is our new dimension x prime. And it is a linear combination of x and y. So now we find a new orthogonal vector, which is y prime. And y prime, as I said, has to be orthogonal. So the angle between our x prime has to be 90 degrees. And so now we can project our data points, as we did before, on y prime. And so what we get now, if we take x prime and y prime, and we use those as our new dimensions, let's just now work in the space of x prime and y prime. So we have a newly aligned data set. The data points are exactly the same. They haven't changed. Their relationship to each other is unchanged. So the distance between this point and this point is the same in x prime and y prime as it was before with x and y. But what we can immediately see is that the most variance is captured by x prime, and then a little bit less variance is captured with y prime. And so this is the key thing about principal components analysis. We have dimensions that are sorted by the variance that they capture, and they are also independent of each other. Y prime and x prime are uncorrelated. Now we want to reduce dimensionality. In this case, we have two principal components, or these axes, these dimensions. So now we can remove the dimension with the lowest amount of information, and this is y prime, and we would be left with x prime. So now we only have the values of data points on x prime. So we reduced our two-dimensional data to a one-dimensional data set by keeping the most amount of information that we can with a single dimension. All right, what do you think? Is this like somewhat making sense? Okay, so maybe in the next video we can like go into the math. I think that was a yes. So there will probably be a second video about a more in-depth analysis of how the math works. And then we also can add some examples of how you can visualize high-dimensional data. How does that sound? All right, so this was just supposed to be a very short introduction of the concepts of principal components analysis. I hope it is helpful to you, and I'll probably make a video that includes more math and the motivation from a theoretical point of view. And I hope to see you next time, and see you soon.